Hi, in today's video we are going to study algorithm for decision tree. We will see how to prune different methods for decision tree. We will also look into strength, weaknesses and application of decision tree. Followed by we will see working of random forest method, how out of bag OOB error is standing in random forest method, followed by strength, weaknesses and application for the same. So let us start with decision tree algorithm. Algorithm of decision tree takes input as two parameters. First one is the training data set, as well as it requires test data points or test data set. Along with training data, it will prepare some decision tree, and using test data, it will check accuracy by predicting class label and comparing that label with the known label of test data. So first step inside decision tree is that we have to repeat some set of steps for all attributes. That means if a dataset contains n attributes, this loop is going to get executed n number of times, one for each. So we will do for each and every attribute one at a time. We calculate the entropy EI for an attribute Fi. Then we will first compare E of I, that is entropy of ith attribute, whether it is lesser than entropy, minimum entropy. So before this particular loop, we set our minimum entropy as to infinity or to 100. So any attribute which is having lesser entropy than the minimum one, then we set minimum entropy as EI and minimum attribute as Fi. After this loop, we will repeat these set of steps for all each and every attribute. So at the end of this loop, we will have f of min, that is an attribute which is having minimum entropy, and we will also have e min, that is an entropy of a feature I. We all know that if feature is having lesser entropy, the larger the information gain. That's why we need to split our partition or our original data set using that particular attribute. So F min will give us the minimum attribute which is having minimum entropy, hence it will have largest gain. So we will split our data set into subset or partition using an attribute F min, and we will make a decision tree node that contains an attribute fmin, and we will split the data into subset. Say for example our data is consisting of an attribute, say programming skill, and that programming skill value is poor, good and excellent. Okay, and let us assume out of all different features, this feature is having minimum entropy. So we will make a decision tree node. So in a decision tree, we will make a node that we call as programming skill. And that programming skill node will have three different branches because we have three different outcomes or three different values under attribute. One is poor, second one is good, and third one is excellent. So this is what the statement this says, that draw a decision tree node containing an attribute fmin, because out of different attribute this was the minimum, and we split the data set into subset, and in the last step it says that we have to repeat above given steps unless and until full tree is drawn covering all attributes of original data set. That means we need to split this particular node into subset, this into different subset and this into different subset with the help of repeating steps right from here to here. So this is a decision tree algorithm is. Now let us understand overfitting of decision tree. So if we apply stopping criteria of a decision tree, that we allow a tree to grow indefinitely. That means tree will keep on growing unless and until each and every attribute having different possible values and its all branches are covered. So in such cases, These feature divides our tree into smaller portion and subtrees are generated accordingly. And that will result in something called as overfitting. So overfitting of a data will give you a good result in a terms of training, but in terms of testing or for validation, it might give you some larger error. So it is important to avoid overfitting of decision tree, and this avoiding overfitting of decision tree is done with the help of process something called as pruning a decision tree. So pruning reduces the size of decision tree so that our decision tree model is more generalized, and it will classify your data set with labels in a better way. So your predictions will be more accurate. There are two different approaches to prune a decision tree, something called as pre-pruning and another approach is post-pruning. In an approach of pre-pruning, we stop growing a tree before it reaches to perfection. That means before tree starts growing complete way, we apply some stopping criteria in between, such as minimum threshold entropy or minimum information gain in order to split a particular branch or not. So these kind of stopping criteria will be introduced, and at the time of generation of tree only we will always check our threshold limit. If it is satisfying entropy or satisfying information gain, that only we will apply a tree to allow a tree to grow. Otherwise, we will limit itself on that level only. In contrast to post pruning, we allow tree to grow completely, and later on we apply or we remove or prune some branches of decision tree. So there are two different approaches. In the first approach, we stop a tree from further growth once it reaches to certain number of decision trees. So before the starting, only we have to decide what will be the number of decision tree nodes that we would like to introduce in our decision tree model. And this strategy avoids overfitting as well as it optimizes computational cost because it reduces the cost of computing unnecessary nodes. And here we have the chances of ignoring very important information which is being contributed by a particular feature. Since we have only limited number of nodes, it might happen a feature which might contribute later on very more. In order to predict the label, we might ignore those kind of features. So it is complete possibility that of skipping a feature which is contributing more into prediction. And this particular approach might result in missing out certain pattern of data. So the information which is contained inside data is not captured correctly in a decision tree model. In contrast to pre-pruning, there is a post-pruning. In this approach, we allow tree to grow in its full extent. And later on, once tree is fully grown, we apply some criteria, say for example, error rate of nodes or number of nodes that are allowed or minimum information gain. Those kind of things can be help us to prune or eliminate some of the nodes. So the size of the tree will be reduced based upon this selection criteria, and this will give you more effective in terms of classification accuracy. Here we actually considering all minute information that is available in data, in our training data, and that's why even though it is computationally more expensive, but will give you a better result. Now let us discuss different strengths, weaknesses and application of decision tree. First of all, decision tree produces very simple, understandable rules. If data is very simple for which we are making a small decision tree, we have very less mathematical and computational efforts that are required. And decision tree basically works for most of the problems. It can handle numerical as well as categorical data very well. And the size of training data doesn't matter. Decision tree will work very well even your training data is small or whether it is very large. And it gives us a definite clue of whether feature is powerful or not by calculating its entropy and deciding splitting up based upon information gain. Decision trees are often biased towards a feature which is having more number of possible values. It gets overfitted very easily. That's why pruning is essential in decision tree. They are more prone to errors in classification problem with many classes. So if your training data is very less and comparatively your number of classes in prediction are very large, then there are possibly chances of errors or error rate is high in terms of decision tree. They are computationally expensive to train because in reality training data is very large and number of classes or target classes are also very more. And larger trees are very complex to understand. These rules are not as simple as that. Now, different application of decision tree. You can apply this model to fit a data set which is having finite list of attribute, and it only can't be applied to that data which consists of infinite set of loops or infinite number of attributes. And we can also apply to that training data set which might contain more possible number of missing values or outliers in a given data. So most of the applications decision tree can fit in. Now let us understand another method which is an ensemble method of decision tree that is called as the random forest classifier. So basically this technique is an ensemble technique which combines multiple classifiers to make a single model. The type of classifier that it combines is nothing but a decision tree. So different decision trees are built and they are combined into a single model, and that model is called as random forest model. Here ensembling is usually done using a concept of something called as bagging. Bagging with different feature set. Remember, bagging is also known as or works with the concept of simple random sampling. So here we make different portions or different subsets out of given training data, and accordingly we make different decision trees. Here not a single decision tree is prepared, we have large number of trees in random forest to train our model in such a way that contribution for each and every feature comes and to a respective number of models. We call a method something called as bagging, which is nothing but drawing a random sample out of given set of data. Okay, so drawing a random sample. So this is the simple random sampling. Okay, so this is the method which is used by bagging technique. We draw different random samples and generate subset of our test data. So this is the test data and its random subsets are generated, and these random subsets are used to make a tree that corresponds to a particular random subset. Likewise, second tree is built with a correspondence with in a correspondence with second subset, and likewise nth subtree is calculated, nth decision tree is calculated or built upon the random subset number n. Here as you can see there are different number of decision trees, hence they can classify a given input data into any of the class. So whatever the output is produced by that particular decision tree, we make majority voting out of it. So if different two trees are saying class 1 and only one tree is saying class 2, whatever the final class is there will be based upon the majority given by each decision tree. So here in random forest, after generation of decision tree based upon random subsets, we combine these trees and at the end something called as majority voting is applied. Now as you can see, what is the procedure of random forest? Let us look into the detail. So as you can see here, there is a training data set and we apply something called as bagging, which is nothing but bootstrap sampling. It is using, which is nothing but simple random sampling with replacement. Okay, now these bootstrapped samples are used to make different decision trees. So in very first step, we have to consider how many attributes are there in a given original training set. So say for example, feature 1, feature 2 up to there are capital N features are there in original training set. So we have to select at random any M attributes or any m features where m is lesser than n. So out of this capital N number of attributes, we are only selecting m attributes randomly, and those random attributes can be up to Fm will be here in first random sample, and we use best split principle on these M features and calculate number of nodes. So using this sample, we have to calculate number of nodes that will be used to create a decision tree for this particular random sample data. And using that sample, we have to keep splitting our node into child node until a tree is grown to a minimum extent. So whatever the procedure of decision tree growing is, that will be applied in order to generate a first decision tree. And later on, in next step, we have to select a different subset of training data, something called as with replacement. As you can see, the word replacement that gives us the idea of simple random sampling with replacement. That is nothing but the concept of bagging. So again, out of this 1 to nth attribute, we have to select any m attribute such that m is lesser than capital N, and those many attributes can be here later on considered as a bootstrap sample 2 or a subset of training data 2. And using these set of attributes, we have to generate another decision tree. And we, before growing a decision tree, we can also set number of nodes that we would like to incur in our decision tree. Later on, we keep on exploring a tree unless and until it is fully grown. And again, we will repeat these steps. That is the steps number from 1 to 3 for another drawn random sample. And how many times this process will continue? So we will continue this process small n times. So remember, this is nothing but nth tree. Okay, so this is the tree 1, decision tree 1. This is our decision tree 2, and likewise we have decision tree n. And likewise we can have any number of decision trees in between. And whenever there is a test data or any unknown label data, so any unknown data is given to each and every decision tree at the same time, and we will test conditions according to this, and we will follow the path in order to get its final result. Say for example, this particular decision tree gives a prediction of an output label of unknown data as class 1. This says it is class 2, and this says it is class 2 for example. So here at the end we will consider all inputs and given it to majority voting. Whatever the output is there, that will be considered as our final class. So this is how our random forest tree works. Let me discuss out of bag error in random forest. So what is basically out of bag OOB error in random forest? So basically we are here using bootstrap sampling to construct a tree. So there are always some samples, some attributes or some rows that are missed, which are considered in a subset of data. That a sample that we are drawing from original set. Some sets are there, some data sets or data points are there which is left to be considered in a particular subset. So those left out sample of a bootstrap which is not used in ith construction of a tree. That means that sample might not be used here, or it cannot be used here or not used here. From any sample or for any construction of ith tree, if that sample is not used, we can use that sample as in test data or validation data to measure the performance of a model. So we will consider those kind of samples and we make a prediction of a complete random forest based upon that left out sample, and that prediction is evaluated and it is tallied according to its original label. And we here not only consider the class label of each individual class, but we must mind that always we consider the final label. So this final label is evaluated against its original label. So that particular, if any error is found in a prediction of final label to the original label, that value or that particular thing is termed as error. So in a random forest, total error rate of a prediction is nothing but a sample which is termed as out of bag error rate. So this particular error rate is nothing but an error rate which is is in result of left out sample because of bagging, that is termed as out of bag error. Let us discuss strength, weaknesses and application of random forest. Strength of random forest is that it runs very efficiently on large and expensive data set, which is having larger number of attributes. It is the robust method for estimating missing data, and it also maintains the precision with large portion of data is absent. That means we can use random forest even though if your data contains a majority part is missing, and it is one of the powerful technique for balancing error in class population of unbalanced data. It estimates out the features which are most important since it makes use of decision tree, hence entropy and information gain will be there. It also generates internal biased estimate of generalization error as a forest generation process. And this random forest method also works very well for classification as well as for regression problems. Now, weaknesses of random forest is that it combines number of decision trees, hence the rules are very complex and very difficult to understand. Since it is having more than one decision tree, it is computationally expensive. Now, applications are that we can apply random forest model to most of the classification problems that are known. So basically, it is very popular among the wide range of classification problem, which gives a very good result. So that is all for today. In today's video, we have seen decision tree algorithm. What are the different approaches of pruning a decision tree, strength, weaknesses, and application of decision tree. Along with that, we have seen how random forest work and strength, weaknesses, and application as well as out of bag error of a random forest. That is all for today. Thank you everyone for watching this video. This is Munira Dobia signing out.